Okay, hey guys. So let's do a little bit more detail on how to tell from a structure if your acid is going to be stronger or weaker. So we've talked about this a bit, but in order for an acid to be an acid, it donates a proton, right? That's how we generally define it. And all the acids that we actually like talk like that are a thing, like all the acids, um, are actually like covalent molecules with a H bond, with some kind of bond to a hydrogen. So how easy is it going to be to lose that hydrogen? It depends on the strength of that H bond. So just to kind of draw out a reaction, like what actually happens when a reaction happens and we lose a proton or a proton is transferred to a base. It's usually and if you ever do OChem, like this is like a basic intro to like some of the stuff you do there. But usually a lot of the bases will have a lone pair or something like that, and that lone pair will come and react with the hydrogen, and then the electrons from that bond will just get like pushed onto the conjugate base. So our products end up looking as you would predict. You have your Cl ion, and now you have that protonated ammonium. So that's kind of like what these reactions like actually look like. Um, which I think is interesting, but not something you'd have to like draw for this class. So let's look at a few examples to kind of illustrate how are we going to make these comparisons, like what factors should we care about when considering the strength of these bonds. So I'm going to just highlight all my acidic protons, um, my acidic hydrogens. That way we can like think about like what bond are we trying to evaluate here. Um, like I've tried to point out, like hopefully it will be obvious from the structure, especially as you like keep doing this. It will usually be like one of these where it's like attached to an O, or it'll be like the obvious like hydrogen out that's like in the front of the formula. And yeah, they should be clear to recognize, especially for this class. Um, okay, so what factors should we take into account? Um, these kind of acids, these ones where it's just like basically just the halogen ones, where it's just a proton and then one atom. They're called binary acids because there's two things. So just for these specifically, the factor that we really want to consider is atomic size. Okay, so let's look at these two things. We have a proton on bromine and we have a proton on iodine. So which one gets to be the more acidic one? So let's consider this, as you know from your trends, or hopefully expect. Iodine is our bigger molecule, or bigger atom, right? Lower on the periodic table. So what does that do to strength? We've talked about this before, but you might recall from like those graphs, the ones that like went like that or that. The ones where it was like one axis is distance between the two atoms and one axis is like the energy in that bond. Might recall that if we have more space in between, if we've spread out our nuclei, so here, let me write that out. Since iodine has a larger radius, So since things are more far apart, we're really like stretching that bond, right? Like it's bonded, but like that iodine is like the nucleus is way over here. It's barely holding on to those shared valence electrons. So that will render this a weaker bond. Which means that HI is the stronger acid. Okay. So this factor really only matters if we're like comparing if we are comparing the oh no, that's not what I want. Where's this thing? If the thing attached to the hydrogen, so the thing actually involved in the bond has a size difference, it's not about the molecule size. So this is more a rare factor for us to consider, but something to keep in mind. Okay. Another thing we might consider is electronegativity. Okay. The ability to pull on electrons. So let's compare these two structures. What do you notice that's different about them? And hopefully we see that we have this oxygen embedded in the carbon chain versus the other one just being a carbon chain. So what does that do? This oxygen is more electronegative. So electronegativity, pulling on electrons. So, I think we kind of think of it as like when we draw a Lewis structure, we're like, like these bonds are between those two atoms, and these bonds are between those two atoms, and these bonds are between those two atoms. Which, yes, that is mostly true, but it's more complicated than that. Um, and even a atom over here could affect these bonds. Um, like an attractive, like, if I put a magnet like over here, like maybe those electron, like the other magnet isn't gonna like whoosh over to it, but like maybe it will like inch that way, like if you ever done like the iron shavings thing and like started to hold a magnet like closer and closer. It does have an effect, even though it's not right next to our bond of interest. Oh yeah, here I'll highlight that acidic proton again, just so we know what we're considering. Okay. So more electronegativity, pulling on electrons. Electron density is pulled towards the central oxygen. And if we're pulling that electron density away from other bonds, away from other parts of the molecule, that is going to render those bonds weaker. So more electronegativity in your structure is going to increase your acidity, because it'll generally weaken those bonds. Alrighty. How about this one? We recognize those two common acid structures, seeing an OH at the end of your structure or seeing COOH. And again, this is what those Lewis structures actually look like if you see that pattern. So this is our acidic proton in this structure. And if you have this group, this structure, that's your acidic proton. but it's attached to, we've changed what that carbon is attached to, right? We can see that the difference between these two structures is this part. Um, so, kind of like that, what we just went over, the electronegativity thing, like that's also an explanation here. Like, these are both of the things we're going over. A lot of the time you could use both. But there's something else going on here that has an even bigger impact. Let's consider resonance. Okay, so looking at these guys. Um, and for me, I like when I'm assessing an acid strength, a lot of the time what I'm actually thinking about is like, what is it going to look like as a conjugate base? Like, what happens to this thing? Like, well, what does it look like as a conjugate base? So here, I'm just going to show those and then we can consider like what factors are in play here. So again, if it acts like an acid, or yeah, if it acts like an acid, something is going to come and take that proton, and then those electrons are just going to end up going onto those oxygens. So these acids are in equilibrium with their conjugate bases, which for this one would look like this. And for this one would look like this. Okay, so let's look at this. Sorry. Sorry. Okay. Anyway. Okay, so here are two conjugate bases. Which one is more stable? Which one can handle going through this change? Which one can handle losing that proton and still being okay? That's kind of like how I generally think about these guys. So let's look at this. In this structure, we lost that proton. The oxygen got the electrons from that shared bond, and now there's this negative charge, these extra lone pairs centralized on that oxygen. And this structure is just like a carbon chain. So those electrons are really just sitting on that oxygen. Which is okay, but like it's not very stable. Like, that's we're increasing the density of like energy in that space. The formal charge of this oxygen isn't right. Like it's just like it increases the stress of the system. Um, so, this isn't like that stable of a structure. So, it could lose that proton, it could act like an acid, but when it does, it's a little unstable. Um, versus, let's look at this one, almost the same structure, but instead we had the COOH group. It's called a carboxylic acid, but you don't need to know that. Um, and that versus just having the OH, the alcohol group, that's what it's called. Um, so let's look at this. Again, we have that negative charge on our oxygen now, but hopefully we recognize this is not the only structure. There is resonance going on here. In reality, it's not just this structure, and it's not this next structure I'm going to draw. It's going in between these two structures. So let me draw it out in case you don't see it. This is in resonance. Also notice how my resonance arrows and my equilibrium arrows are distinct. I know both are back and forth, but this should look different. This is in resonance with a different form of this acid. these electrons could go and be a part of this bond, forcing those electrons to move up there. Okay, so hopefully we recognize that those are two forms, resonance structures of this atom, and in reality, we're moving back and forth between them both. So that negative charge is not actually just on one oxygen or the other. It is spreading throughout this whole thing. It's constantly moving in between these atoms. So the fancy word for that is that the resonance forms allow it to be delocalized. This means that we have a more stable conjugate base. We've like decreased the energy, like electrostatic burden of having those extra electrons. And when I say more stable, whenever we say stable, we're pretty much that's pretty much like um akin to saying like reactive. So this is a more stable, less reactive, aka weaker base. So I'm not going to talk very explicitly about telling if a base is stronger or not. And like the more detailed way of doing that is like beyond the scope of this class, but it's basically just the opposite of what we're going over for acids. If we evaluate, oh, this one's the stronger acid, the other one must be the stronger base, you know? Okay. Okay, so we have a more stable conjugate base, which means HA, this original, here, I'll just write out the full formula for it. Is the stronger acid. It's able to be more acidic. It's able to lose this proton more easily because the form we get left over with is more stable. This process of changing from this form to this form is more favorable. Okay. Okay, let's look at one more example. We have these two. And looking just at the formulas, you probably know which one's stronger, but let's talk about the structures. Or you could pause the video, honestly, try this one on your own. This one we could use either explanation to kind of to explain it. Let's look at this. So I don't know, there's multiple ways we could go about it. You could say um additional electronegative oxygen. Pulls electron density. And weakens that the bond. Okay, so we could do that. Or maybe you realize that, yeah, I'll draw it for you. This guy's conjugate base, we would just be left over with something that looks familiar to us, our nitrate ion. or sorry. So this could be in resonance with itself also. That single bond could be on any of these oxygens. So this has three different resonance forms versus if we lost this proton and we're just left over with this part, that would just have two resonance forms. So this has more resonance forms. The conjugate base, NO3 minus, has more resonance forms. More delocalized charge, which leads to a more more stable NP, which is stronger. Yes. Okay. So again, if we wanted to do the opposite, this one is the weaker conjugate base, and this one would be the stronger conjugate base, right? So if we're assessing base strength, we would just use the same reasoning, looking at the base form, the conjugate bases. Just think about what you would do to tell if that was a good acid. And then that one's the stronger base, or the one that's like wouldn't be a good conjugate base for an acid, is going to be the one that is more likely to act like a base and regain that proton. Yeah. So that's kind of it. Those two factors. Um, there we go. Let's look at this. We've talked about this before, but I just wanted to kind of clarify it again, just in case it hasn't been clear. We kind of alluded to it when we're doing our titrations, and I have briefly mentioned it when we've done it in the past, but just to kind of focus on why does it matter, which base, being able to tell which acid is stronger, we need to understand what that's going to do to our reaction. So as we have talked about, if we know an acid is stronger, a stronger acid is more likely to act like an acid. It's more likely to donate that proton, act like an acid. So we could compare acid strength. Now you know the way to do it with structure. Or if you're given KAs or pKas. Okay, so here we have a scenario. We are mixing together oxalic acid, I'm pretty sure it's called. That guy. With our first deprotonated sulfuric acid. Okay. So we're given a big table of Kas. So just gonna look at that first. When these two come together on this side of the reaction with these two reactants, which one is gonna act like our acid? So let's identify our Kas. We have this guy versus this guy. Okay, and we can clearly see that on this side of the reaction, that's our stronger acid. So that's the one that's going to get to deprotonate. Okay, so that's how we could predict what would the products be. Okay, but But then this question is asking, will the products or the reactants be favored when the reaction happens? So to do that, we've now formed, we have our, here, let's label all this. We have our acid, our base, our conjugate acid, and that no longer has that charge, sorry, and our conjugate base. Okay, so both sides of the reaction now have an acid and a base and an acid and a base. Which reaction is more favorable to happen? So in order to do that, we have to either compare your bases or compare your acids. So let's compare our acids. Which of these acids is the stronger acid? That's the one that gets to act like an acid. That's the reaction that gets favored. So let's see. What we're comparing is we're again looking at this one and we're comparing it to this one. Okay, look at those Kas. Which one's your stronger acid? This one is the stronger acid. Which means this reaction, the reverse reaction where this gets to act like an acid, is going to be more favorable, which means at equilibrium we would have reactants favored. So, like we've done many times, if it's reactants favors, we could also be given, like, what if you were given KEQ or KC? You would expect that to be less than 1. So, you could be given, maybe you're not given all the Kas, but you're given this. Could you tell which acid was stronger based on that? It would just be this process, but backwards. So something to keep thinking about. Okay. Finally, we have one more section here. We talked about this already with titrations, but just to clarify, what is the relationship between pKa and pH? And this is really relevant for like just titrations is what we're talking about here. So let's focus on weak acid and strong base first. If we were adding a weak acid to a strong base, that's this reaction. Weak acid plus our strong base going to form the conjugate acid. Sorry, the conjugate base and water. So as we add more of the titrant, I feel like this is part of why I wanted to do all those ice tables and stuff when we talked about titrations. Like you can go back and see it, so like look back at your math. But as we keep doing this, as we're adding more and more of this, we're reacting with this, we're using up this acid, reacting it, and forming more of our conjugate base. So as the reaction goes along, we're getting more and more of that conjugate base. And like we talked about before, a very important part of our titrations is, yes, that equivalence point, which would be here when we get that straight shoot up, when we have completely reacted with all of that acid. But another important part of our titrations is what happens when we've added half the volume of our equivalence point. And so like we've talked about before, and this is just based on the Henderson-Hasselbalch equation, you could look back at when we did that math. But at the half equivalence point, our acid concentration is equal to our conjugate base concentration, which means that the pH at that point is equal to pKa. So right here at that point, that is pKa for whatever acid. Okay. So something just to clarify that we didn't like explicitly talk about is that also means so we're moving towards this point. As we're adding more and more of that base, as we're continuing to titrate it, we are using up our acid, forming more of that conjugate base until we get to a point where they're equal. And then we keep adding acid, right? We're trying to get to that equivalence point. Or sorry, we keep adding base, we're trying to get to that equivalence point. And as we continue to keep doing this reaction, keep adding more of this, we are forming more of this. So as you keep going past that point where they're equal, and hopefully this sounds reasonable, and slash we saw the math with it when we did all those calculations. Before we get to that point, the concentration of HA is greater than the concentration of the conjugate base. And if we go past that point, then that is less than the conjugate base. Okay, so let me show you that on here. So here's our point where pH is equal to pKa. For this, oh yeah, and here, a reminder that this region, as we saw with our calculations, is called the or I'll tell you now that this is called the buffer region. So only in that first flat part, that's where this matters. That's where you have both conjugate acid and conjugate base, and where we could use Henderson-Hasselbalch like we saw with our calculations. So in this region, there's two sections. From here to here, we have our conjugate acid being in more abundance. And here we have our conjugate acid being in less abundance. Oop. And after we get to our equivalence point, right, like we're not going to have any of that original acid anymore. So again, to reiterate, this is at a pH lower than pK. This is at a pH higher than pKa. Okay. I did want to clarify, what does this look like for bases? So I misspoke in class, so I just wanted to clarify. This point in the reaction for bases is still pKa. Okay, just from Henderson-Hasselbalch, because usually what we're graphing here is the pH. pH is equal to pKa when we're at half the equivalence volume. And I feel like that's kind of hard for some of us to think about, especially when we're like starting to think about like acids versus bases, like conjugate acid, conjugate base, like how do those behave? But I'm hoping that I'm hoping we can clarify that. Wow, okay. I guess I'll just talk like this now. That's cool. So at half equivalence point, we still have that relationship. pH is still equal to pKa. If we were graphing pOH, that could be equal to pKb. But in reality, like we pretty rarely are going to be graphing pOH. So really, we're still using this relationship between pKa and pH. If you wanted to find the Kb, you could then derive it from the pKa based on the relationships we've talked about. Okay, so let's look at that again. When the pH is greater than pKa, right here, let's do it in the same order as before. pH is less than pKa. So same exact relationship as before. When pH is less than pKa, the conjugate acid, here I'll write it the same way we had it before. There's more of it than the base. Okay, and I wanted to take the time to write it out like this because I feel like it's confusing to like, are you thinking of it from the acid's perspective? How can we then try to think of it from the base's perspective? This is acids and bases, these are just opposite processes, right? Like they're partners. Um, so here I could rewrite it like this if you'd like. If we want to think of it from the basis perspective, here's that conjugate base is in higher abundance than our, sorry, that conjugate acid is in higher abundance than our base. So those are like the same thing, whether we're thinking of it from the acid's perspective or the base's perspective. And when we're using Henderson-Hasselbalch, like we're going to practice in the next few sections, they're equivalent, just whichever one is the acid, we can think of as the acid, and whichever one is the base, we can think of as the base. So let's look at that on the graph. When pH is less than pKa, so I feel like this, at least for me, this is like the weird part. So we have, this is our buffer region, right? That first flat part. But on this graph, we're starting at a high pH, right? So this is actually the section where we have pH less than pK. This is where the concentration of the acid is greater than the concentration of the base. And you can write that with the base species if you prefer. Okay. When pH is greater than pKa, then we know that we expect there to be less of the acid. So this just kind of flips on this graph. But that makes intuitive sense, hopefully. And as we keep doing as you keep doing titration calculations, like you'll see this. When we begin a base, if we have base in the flask and then we're slowly adding acid to it, it makes sense that at the beginning we have more of the base species and then we're going to create more of the acid species. So just want to clarify that. I know it is confusing, but hopefully that visual kind of helps. Okay, there's a small example for this. And that's basically all we need to know is just that relationship of like when pH is less, like what does that mean? So let's look at this example. We have formic acid with a pKa of something combined with sodium formate, that the pH is 3.5, which species is in greater abundance. So slightly different from the titration application, but the same concept. Notice that we are mixing together this with this. Maybe you recognize, I know we've only briefly talked about this. This is the acid. This is the conjugate base. We're adding both. This is actually a buffered solution. Okay. So which one is getting favored? It says that we have a pH of this, but a pKa of this. So at this moment, with the certain concentrations of both of those that we added, we have a pH that is less than pKa. And we know that this relationship, and again, I like to remember the relationship. I'm probably going to like, in my mind, I'm visualizing a titration just because that's like the context that I like thinking about. Or you can memorize this, whatever. But pH is less than pKa. I expect to have the concentration of my acid be greater than the concentration of my base. So because of the pH at this moment, I know that the concentration of formic acid is greater than the concentration of that species, the base. Okay. So that's kind of all there is to this section, and that's where I will call it. Thanks for watching this, and see you later.